G'day team, welcome back to another video. So today we are continuing on with our polynomial work, more specifically cubic work. So in the previous video we looked at solving cubic equations. We're now moving on to graphing cubic functions. So this is now looking at chapter 4E in the Hazy 11 Methods textbook. We'll get straight into it. So the most basic cubic function is y equals x cubed. All right, and this looks like this graph here. Okay, so the graph is horizontal at 0, 0 for a brief moment there. Okay, as x gets really large and positive, so if we're going this way, y also gets really large and positive, so it's shooting up that way. So we write as x tends to infinity, so as x gets really big, y also gets really big, so y tends to infinity. We can also say that for the negative version, so as x gets really large and negative, so as x keeps going along to the left of the x-axis, y gets really large and negative as well. So as x tends to negative infinity, y will also tend to negative infinity. So a few properties of y equals ax cubed. So when we've got an unknown coefficient, this a coefficient will determine the shape that we have. So our two types of cubic functions we can have it curvy like this, or we can have it where it's horizontal. But our starting point for our cubic function on the left will be down for a greater than 0, so it moves down to up. For a less than 0, it goes up and then down. Okay, so it's a bit like a positive and a negative gradient. All right, positive gradient looks like that, negative gradient looks like that. So similar sort of thing for the shape of a cubic, my apologies. So as a increases, y equals ax cubed also becomes steeper. Okay, so the graph of y equals ax take b all cubed plus c is obtained by translating y equals ax cubed horizontally b units and vertically c units. So you can actually graph cubic functions from the basic y equals ax cube function by using your translations. Okay, we're not going to look at that today, but it's very similar to graphing quadratics by translations, which we did a little bit of in the quadratics section. So every cubic polynomial must cut the x-axis once. Therefore, it has at least one real root. All right, so your cubic polynomial will always cut through the x-axis once, and you'll see that in a moment here. So I've just whipped up a little table. So our polynomials can take different forms, as you're well aware. So when they're in different forms, their graphs will have different features. So when we have a cubic polynomial in the form px equals a times by x take q multiplied by x take r multiplied by x take s, where q, r, and s are in the real number set, then our graph will look like this. So it will cut the axis at q, r, and s, which are our zeros. Okay, for a polynomial in the form a times by x take q multiplied by x take r squared, where q and r are also in the real number set, it will cut through q, all right, in our linear factor, but it will touch the x-axis in our squared factor. Okay, so it touches at r. For a cubic polynomial in the form a times by x take q all cubed, we will have a cubic polynomial that looks like this, where it's horizontal at that point q, just like we had in the basic y equals ax cubed graph. Okay, so you have that flat zone on your polynomial at this value q. And then finally we have a linear factor x take q multiplied by some quadratic. Okay, and if the discriminant of this quadratic is less than 0, then our cubic polynomial will cut the x-axis at q, but then it won't cut or touch it again. So remember, when we're working with quadratics, and we're looking at how the discriminant affects the x-intercepts. The same applies here. When the discriminant is less than 0, it does not touch the x-axis or cut through. So we only get that x-intercept at x take q. So hopefully you noticed that in all 4 of these versions, we have at least one real root that cuts through the x-axis, okay? So let's go through an example. So using the axis intercepts, graph f of x equals x plus 3 times by x plus 2 times by x take 2. So first we look at the value of a to see what shape our graph's going to take. So in this case, a equals 1, which is greater than 0, so we're going to go with our positive shaped cubic, okay? So the x-intercept is when f of x equals 0, so when x plus 3 times x plus 2 times x take 2 equals 0, using that null factor law, we find that x has to equal -3, -2, and 2. So these will be our x-intercepts, and our y-intercept is when x equals 0, so y equals 3 times 2 times -2, which is -12. All right, so with those 4 bits of information, so 1, 2, 3, 4, we can graph our cubic. So coming down here, all right, so making sure we have a nice scaled y-axis and x-axis, okay, so I could probably even input just a little 3 there just to showcase that positive y scale, okay. So making sure we're labeling our axes, all right. So what I like to do, I like to put a little point where my intercepts are, okay, and then we're almost just playing connecting the dots, all right. Because a was positive, we start down here and we're moving up like that. Also make sure you are labeling your graph, okay. Putting that function equation onto your graph is super important. All right, example number 2. So now we're going to do the opposite. We're going to be given the graph and we're going to find the equation of the cubic with that graph. So the graph we're going to be looking at is this one here. So straight away we can see that it's cutting through -3, y-intercept is -16, and it touches at 4, x equals 4. So because it cuts the x-axis at -3, we get a linear factor, which is x plus 3, okay? When it touches the x-axis, like it does at 4, we get a squared factor, x take 4 squared, okay? Now, hopefully you remember just above, if we just scoot back up here, see how when we have this x take r squared, we get it touching, so we're using a polynomial, so a cubic polynomial in this form here, all right? So what we need to write, we write y equals a, so we don't know that a value just yet, x plus 3 for our linear factor, and x take 4 all squared for our squared factor. So now we have to find this a value. So there's one other bit of information on our graph we are given, and that is the y-intercept. So when x equals 0, y equals -16. So -16 equals a times by 3 times by -4 squared. So -16 equals 48 times a. Therefore, a equals -1 on 3. So all we have to do now is substitute that into our equation, and this is our final equation for the cubic polynomial that was graphed above. All right, please have a crack at some questions in 4E, and we'll see you guys next time for another video.